There is a moment that has no name. It arrives without warning. It cannot be predicted from the outside, not by any telescope ever built, not by any instrument humanity has yet conceived. It does not announce itself with a tremor or a flash or a change in the light that reaches us across the dark. From a distance of 19,000 light-years, the star looks exactly as it always has, a smoldering, bloated infrared presence buried behind curtains of galactic dust, pulsing slowly in the darkness of the Scutum Centaurus arm. Nothing in its outward appearance betrays what is happening in its deepest interior. Nothing in the way it glows, the way it sheds material into the surrounding space, the way its enormous envelope swells and contracts over centuries, gives any indication that the process sustaining it is approaching its absolute terminus. And then, in a fraction of a second, it stops. Not gradually, not with a warning. The core of this star, a sphere of iron roughly the size of Earth, compressed to densities that reduce a mass greater than our Sun into a volume you could fit inside a major city, simply ceases to generate the outward pressure that has held the star in balance for millions of years. Gravity, which has been straining against that pressure since the very first moment this star ignited, wins instantly, completely, without negotiation. What follows is the most violent event a single star can produce. But to understand why that moment arrives, and why it is iron specifically that triggers it, and why a star the size of Stevenson 2-18, an object so vast its surface would encompass the orbital path of Saturn, if placed where our Sun sits today, must inevitably arrive at this exact ending, you have to understand something about the nature of stellar fire that most people never learn. Because the fire burning inside a star is nothing like the fire burning in a candle or a furnace or a forest. It operates on completely different principles. It is subject to completely different rules. And unlike every fire you have ever encountered in your life, it does not simply go out when the fuel runs low. It explodes. The story of how stars die begins with the story of how they live, and the story of how they live begins with a single, elegant truth that took centuries of human inquiry to uncover. Stars are not burning in the chemical sense. They are not combining carbon with oxygen the way wood combines with oxygen in a fireplace, releasing heat and light and leaving ash behind. That process, combustion, releases energy by rearranging electrons in the outer shells of atoms. It is a surface phenomenon, a reshuffling of chemical bonds. It is, by the standards of what actually powers a star, extraordinarily feeble. What powers a star is something far more fundamental, far more violent, far deeper in the architecture of matter. Stars generate energy by fusing atomic nuclei together, by taking the cores of lighter atoms stripped of their electrons, reduced to bare protons and neutrons hurtling through a plasma at millions of kilometers per hour, and forcing them close enough together that the strong nuclear force can grab them and bind them into heavier nuclei. This process, nuclear fusion, releases energy not by rearranging electrons, but by converting a small fraction of mass directly into energy, according to the relationship Einstein described in 1905, with an equation so compact and so devastating in its implications that it can be written in 5 characters. The energy released by fusion is not slightly greater than the energy released by chemical combustion. It is not 10 times greater or 100 times greater. It is roughly 10 million times greater per unit of fuel. A kilogram of hydrogen undergoing fusion releases the equivalent energy of burning approximately 10 million kilograms of coal. This is why stars can shine for millions or billions of years on what amounts, by cosmic standards, to a finite supply of fuel. The energy density of nuclear fusion is almost incomprehensibly higher than anything available through chemistry. But fusion is not free. It requires conditions that exist nowhere on Earth, outside the interior of a nuclear weapon. To force 2 hydrogen nuclei close enough together for the strong force to take over, you must first overcome the electromagnetic repulsion between them, the fact that both nuclei carry positive electric charge, and like charges, repel each other with a force that increases as the distance between them decreases. At ordinary temperatures and pressures, This repulsion is insurmountable. Hydrogen nuclei simply bounce off each other, never getting close enough for fusion to occur. Inside a star, the conditions are different. The pressures are unimaginable. The temperatures at the core of an ordinary star like our Sun reach approximately 15 million degrees Celsius. Under these conditions, the hydrogen nuclei protons move so fast, collide so violently, that quantum tunneling allows a small fraction of them to pass through the electromagnetic barrier and fuse. The result is helium, and the energy released by this conversion is what pushes outward against the star's own gravity, maintaining the equilibrium that allows the star to exist as a stable, long-lived object rather than collapsing immediately under its own weight. This balance, gravity pulling inward, fusion energy pushing outward, is the fundamental transaction of stellar existence. Every star you have ever seen in the night sky is a site where this transaction is ongoing. Every point of light above you is an object holding itself up by burning, and every fire, no matter how vast, eventually runs low on fuel. For a star like Stevenson 2-18, a star born with perhaps 25 to 30 times the mass of our Sun, the hydrogen in the core does not last for billions of years the way it does for smaller stars. The crushing weight of so much material pressing inward demands higher core temperatures to maintain equilibrium. Higher temperatures mean faster reaction rates. Faster reaction rates mean the fuel burns through more quickly. A star this massive may spend only a few million years on the hydrogen-burning main sequence, less than 1,000th of the time our Sun will spend there before the hydrogen in the core is exhausted. When that happens, the core contracts, it heats up, and when the temperature climbs high enough, a new fuel ignites. Helium. The ash of hydrogen burning becomes the fuel of the next stage, helium nuclei, which are heavier and carry more electric charge than hydrogen nuclei, require higher temperatures to fuse roughly 100 million degrees Celsius. But the contracting core reaches those temperatures, and helium burning begins, producing carbon and oxygen. The star restructures itself around this new energy source. Its outer envelope expands. Its surface cools and reddens. It becomes what astronomers call a red supergiant, the bloated, cool, luminous category of object that Stevenson 2-18 represents today. But the principle that applies to hydrogen applies to helium as well. Eventually, the helium runs out, and then carbon ignites, then neon, then oxygen, then silicon. Each stage requires higher temperatures than the last. Each stage produces heavier ash that becomes the fuel for the subsequent stage. Each stage lasts for a shorter time than the one before it, because the energy released per unit of fuel decreases as the nuclei grow heavier, while the star's energy demands remain immense. The numbers compress in a way that should stop you. Hydrogen burning, several million years. Helium burning, a few 100,000 years. Carbon burning, a few thousand years. Neon burning, roughly 1 year. Oxygen burning, a few months. Silicon burning, approximately 1 week. 1 week. The stage that immediately precedes the end of this star's life lasts about as long as a modest vacation. While the outer envelope of Stevenson 2-18 drifts and pulses across a volume large enough to contain the orbits of every inner planet in our solar system, while the star's surface glows at 3,000 degrees and sheds material into the surrounding space at rates equivalent to several Earth masses per year, the silicon in its innermost core is being consumed in a process that will be complete in days. And silicon leaves behind only one thing: iron. This is the moment the story has been building toward. This is the terminus. This is the place in the periodic table where the road ends and the cliff begins. To understand why iron is the element that kills stars, you need to understand something about nuclear binding energy, the force that holds atomic nuclei together, and the energy you get back when you either split heavy nuclei apart or fuse light nuclei together. There is a curve. Physicists call it the binding energy curve, and it describes, for every element in the periodic table, how tightly bound each proton and neutron is within its nucleus. The curve rises as you move from hydrogen toward heavier elements, meaning each successive fusion reaction, hydrogen to helium, helium to carbon, carbon to neon, releases energy, because the product nucleus is more tightly bound than the ingredients. The tighter the binding, the lower the energy state, and the difference in energy states is what gets released as radiation, as the light and heat that allow a star to exist. The curve peaks at Iron 5-6, with 26 protons and 30 neutrons, is the most tightly bound nucleus in nature. It sits at the absolute bottom of the nuclear energy landscape. You cannot extract energy from iron by fusing it into something heavier, because the heavier nuclei are less tightly bound. The fusion reaction would require energy rather than release it, and you cannot extract energy from iron by splitting it apart, because splitting less stable nuclei than iron requires energy rather than releasing it. Iron is, in the most precise physical sense, a dead end. When the silicon burning phase ends and the core is composed primarily of iron, the star has reached a state that no previous crisis in its history has prepared it for. Every previous fuel exhaustion was followed by core contraction, heating, and the ignition of the next fuel. But there is no next fuel. The iron core cannot be ignited. No amount of gravitational compression, no increase in temperature, no increase in pressure will cause iron to release energy through fusion. The more the core contracts, the more energy it absorbs rather than releases, accelerating the collapse rather than arresting it. The star has been alive for millions of years. It has survived every previous crisis by finding a new fuel, a new equilibrium, a new way to hold itself against gravity. Now, for the first time in its long existence, there is nothing left to find. The iron core grows. Silicon shell burning continues above it, raining more iron ash down onto the core from above, adding to its mass gram by gram, minute by minute. The core grows hotter and denser as it compresses under its own weight. At a certain threshold, a mass of approximately 1.4 times the mass of our Sun, a value known as the Chandrasekhar limit after the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who calculated it in 1930 at the age of 19 while traveling by ship from India to England. The iron core can no longer support itself against gravity, even in principle. Chandrasekhar was 20 years old when he published the result that would eventually earn him the Nobel Prize. His colleagues initially resisted it. The implication was too extreme, too final. A core that cannot support itself must collapse without limit. There is no stable endpoint. There is no new equilibrium waiting on the other side. There is only collapse, accelerating, irreversible, complete. He was right. And somewhere in the Scutum Centaurus arm of the Milky Way, inside a star so vast, its outer layers have never felt the gravitational influence of its own core in any meaningful way. The iron is accumulating. The clock is running. The Chandrasekhar limit is approaching, gram by gram, in a process that has been underway for thousands of years and will end in a moment so brief it defies the language we use to describe duration. This is the star we are talking about. This is what Stevenson 2-18 is, not merely the largest known stellar object, not merely a record holder in a size comparison chart. It is a dying machine of almost incomprehensible scale, running the final subroutine of a program that has been executing since before the first human being looked up at the night sky and wondered what the lights were. Its death, when it comes, will be the most energetic event in this region of the galaxy in recorded human history. The light from that death is either already traveling toward us or will begin its journey sometime in the next 100,000 years. If you find yourself drawn to questions like this one, questions about what the universe is actually doing when no one is watching, about the physics beneath the spectacle, about the end states of the largest things that exist, do me a small favor. Hit the like button. Subscribe to this channel. It costs you nothing, and it allows this kind of story to reach more people who need to hear it. Get comfortable, turn down the lights if you can. Let's begin. In 1990, an American astronomer named Charles Bruce Stevenson published a short paper that almost nobody read. It was not an especially dramatic paper. It did not announce a revolution in stellar physics or claim a record of any kind. It reported the results of a deep infrared survey of a small patch of the northern Milky Way, a methodical, careful piece of work conducted using the Burrell-Schmidt telescope at the Warner and Swayze Observatory in Arizona. Stevenson had been scanning the galactic plane in the infrared, looking for objects that visible light telescopes could not see, cataloging faint, reddened stars embedded in the dust-choked regions near the galactic center. He found a cluster of objects in the direction of Scutum. He noted that several appeared to be M-type supergiants. He estimated the distance at roughly 98,000 light-years, placed them far beyond the galactic center in the outer reaches of the Milky Way, filed his measurements, and moved on. The paper was 4 pages long. The cluster was catalogued and forgotten. What Stevenson did not know, what no one would know for more than a decade, was that his distance estimate was wrong by a factor of 5. Not slightly off, not within the margin of observational uncertainty. Wrong by 500%, in a direction that made an already remarkable collection of stars seem distant and ordinary, when in reality it was close and extraordinary. The cluster he had found was not 98,000 light-years away. It was approximately 19,000 light-years away, and at that true distance, the stars he had catalogued were not moderately luminous supergiants scattered in the outer galaxy. They were some of the most luminous, most massive, most extreme red supergiants in the entire Milky Way, concentrated in a single cluster, in a way that had no parallel anywhere else in the known galaxy. The correction arrived slowly, the way most corrections in astronomy arrive, not with a single decisive measurement, but with a gradual accumulation of better data from better instruments applied to the same patch of sky by researchers who had no particular reason to expect what they were about to find. By 2001, teams re-examining the cluster with near-infrared photometry began to suspect the original distance was far too large. A detailed study led by Ben Davies and collaborators measured the radial velocities of the cluster members, the speed at which each star was moving toward or away from Earth along the line of sight, and compared them to models of galactic rotation. The result was a kinematic distance of approximately 5.8 kiloparsecs, 19,000 light-years. The cluster was not in the outer galaxy at all. It sat in the Scutum Centaurus arm, one of the Milky Way's 2 major spiral arms, near the point where that arm intersects the northern end of the galaxy's central bar. At this revised distance, everything changed. The cluster, renamed RSGC2 for Red Supergiant Cluster 2, turned out to be one of the most massive open clusters in the Milky Way, containing at least 26 confirmed red supergiant members and an estimated total mass between 30,000 and 50,000 times the mass of our Sun. No other known cluster in the galaxy concentrated this many evolved massive stars in a single location. The cluster's age was estimated at 14 to 20 million years, placing it in exactly the evolutionary window when stars of 12 to 16 solar masses exhaust their core hydrogen and expand into the red supergiant phase. It was, by any measure, a remarkable discovery. But the cluster itself was not the most remarkable thing in that patch of sky. Sitting at the cluster's outskirts, slightly offset from the main concentration of stars, was a single object whose brightness stood apart even in this company of giants. In the 2007 study, it was flagged immediately as anomalous, too bright, too offset, its radial velocity slightly mismatched from the cluster mean. Davies and colleagues classified it as a probable non-member, a foreground or background red supergiant that happened to project onto the same region of sky. In a subsequent 2010 study, astronomer Shuji Deguchi and collaborators assigned it a number within a loose grouping of stars southwest of the cluster core, calling it star 18 inches, a catalogue designated Stevenson 2 SWID. The name Stevenson 2 to 18, often abbreviated as St. 2, 1/8 comes from this second numbering. The same object already carried a different designation, Stevenson 2 DFK1, from the 2007 study. 2 names, 1 star. Immediate disagreement about what it was and where it belonged. What nobody disputed was what happened when you calculated the star's properties, assuming it sat at the cluster distance of 5.5 to 5.8 kiloparsecs. The apparent brightness, corrected for the enormous extinction caused by the intervening dust, translated into a luminosity of somewhere between 90,000 and 630,000 times the luminosity of our Sun, depending on the method used and the assumptions applied. A 2012 study using infrared radiative transfer modeling settled on approximately 440,000 solar luminosities as its best estimate, combined with an effective surface temperature derived from the star's spectral type classified as M6, corresponding to roughly 3,200 Kelvin. The Stefan-Boltzmann law yielded a radius of approximately 2,150 times the radius of our Sun, 2,150 solar radii. The number entered the literature quietly. Then it entered databases. Then it entered comparison charts and Wikipedia articles and YouTube animations and classroom posters. The caveats that surrounded it in the original research, the uncertain distance, the disputed cluster membership, the anomalous spectral energy distribution, were stripped away during this migration. What reached the public was a clean, confident claim. Stevenson 2 to 18, biggest star, 2,150 solar radii, case closed. But a number that size is never simply a number. It is a provocation, and when astronomers began examining the provocation carefully, they found something that should have generated far more alarm than it did. The number violated the rules, not in a minor way, not in the way that a measurement slightly exceeds a model's prediction, prompting a small revision to a parameter. In a fundamental way that placed Stevenson 2, 18 inches direct conflict with two independent theoretical boundaries established through decades of observation and calculation by some of the most careful stellar physicists of the 20th century. The first boundary is called the Hayashi limit. In the 1960s, Japanese astrophysicist Chushiro Hayashi developed a theoretical framework describing the coolest, most extended configurations a star of a given mass and luminosity can maintain while remaining in what physicists call hydrostatic equilibrium, the state where the inward pull of gravity is balanced by the outward pressure from thermal energy and radiation at every layer of the stellar interior. Below a certain temperature threshold, Hayashi showed, a star of given properties cannot maintain this equilibrium. Its envelope becomes fully convective, unstable, unable to sustain itself against the forces acting on it. The boundary defined by this threshold translated into physical radius places an upper limit on how large a red supergiant can grow while remaining a stable, long-lived structure. For stars in the luminosity range of Stevenson 2 to 18, this limit corresponds to a radius of approximately 1,500 solar radii. Stevenson 2 to 18's estimated radius exceeds this limit by more than 40%. The second boundary is called the Humphreys-Davidson limit, established in 1979 by American astronomers Roberta Humphreys and Chris Davidson. Working from observations of thousands of evolved massive stars in the Milky Way and the Magellanic Clouds, they noticed something striking in the Hertzsprung-Russell diagram, the fundamental chart that plots stellar luminosity against surface temperature. In the upper right corner of the diagram, the region corresponding to stars that are both extremely luminous and extremely cool, the chart was almost empty. Stars approaching this region appeared to become violently unstable, erupting in episodic mass loss events that prevented them from climbing higher on the diagram. The boundary drawn through this empty region was not a theoretical prediction. It was an empirical observation, a line drawn through the actual distribution of real stars, marking the territory where stable, cool supergiants simply were not found. When you plot Stevenson 2 to 18 on this diagram using its estimated luminosity and temperature, it falls in the forbidden zone, not near the boundary, in the zone itself. A single measurement placing an object beyond one theoretical limit might be explained by an incomplete model. A measurement placing an object beyond two independent limits simultaneously, one derived from theory, one drawn directly from observation, demands a different kind of attention. Either the star is genuinely extraordinary in a way that requires revising fundamental stellar physics, or something about the measurement is wrong. The scientific community did not, on the whole, resolve this tension loudly. Research papers noted the discrepancies. Authors flagged the anomalous spectral energy distribution, the uncertain distance, the disputed cluster membership. The measurement propagated anyway, carried forward by the momentum of a compelling headline and the absence of any definitive refutation. This is how records work in popular science. They are sticky. They resist revision not because the evidence is conclusive, but because the revision requires more effort than the original claim. Dethroning a record holder demands new data, new analysis, a willingness to publish a result that tells a less dramatic story than the one it replaces. In the meantime, the headline persists, but the tension in the underlying physics persists as well. And to feel the weight of that tension, to understand why a radius of 2,150 solar radii is not merely impressive, but genuinely transgressive, you need to understand what kind of object actually exists at those dimensions, not the number, the thing itself. The physical reality of a star so extended that the word star begins to fail as a description. The surface gravity of Stevenson 2-18, calculated from its estimated mass and radius, is a fraction of a percent of the surface gravity of our Sun, where our Sun's surface holds its atmosphere in place with a gravitational acceleration roughly 28 times what you feel standing on Earth. The photosphere of Stevenson 2-18 sits so far from the star's gravitational center that the pull of gravity there is almost negligible by any standard of comparison available to us. An object weighing 100 kilograms on Earth would weigh less than a kilogram at the surface of this star. The thermal motions of gas molecules at 3,200 Kelvin, roughly 7 to 8 kilometers per second, are not vastly smaller than the escape velocity at that distance. The star's own radiation pushes outward on every dust grain and gas molecule with a force that is, at these extremes, comparable to gravity. The result is a surface that cannot hold itself together. Every convective upwelling, every pulsational expansion, every temporary brightening pushes material over the lip of a gravitational well, so shallow that escape requires only a small additional nudge. The star sheds mass at a rate estimated at roughly 1.35 times 10 to the negative fifth solar masses per year, several Earth masses annually, streaming outward into the circumstellar environment in a river of gas and dust that builds a thick cocoon of expelled material around the star. This mass loss is not incidental, it is structural. The star is not passively aging, it is actively consuming itself, shedding the layers that define its enormous radius, stripping away its own envelope in a process that will continue until the core's final crisis makes the outer behavior of the star entirely irrelevant. The dust envelope, created by this mass loss, is directly detected in observations. Stevenson 2-18 glows intensely in the infrared, far more brightly than its photospheric temperature alone would predict. The excess radiation comes from warm dust grains surrounding the star, heated by the stellar radiation and re-emitting it at longer wavelengths. Silicon emission features at 10 and 18 micrometers indicate oxygen-rich dust chemistry, consistent with the outflows of evolved massive stars. Water mazes regions in the circumstellar envelope, where water molecules amplify microwave radiation through stimulated emission, have been detected as well, requiring the specific density and temperature conditions found in powerful stellar winds. Every one of these observational signatures points to the same conclusion. This is a star in an extreme terminal state, a star shedding its own substance into space with an urgency that reflects the instability of its physical configuration, a star that cannot maintain its current size indefinitely, not because it will shrink gracefully, but because the core burning at its center is approaching the element that ends all burning. It was found by accident, in a 4-page paper almost no one read, by an astronomer who underestimated its distance by a factor of 5. It may be the largest star ever found. It may be somewhat smaller than its headline number claims. The uncertainty surrounding its properties is genuine and deep, rooted in the difficulty of measuring an object this extreme at this distance through this much intervening material. But none of that uncertainty changes what is happening inside it. The iron is accumulating. There is a kind of fire that does not look like fire. It produces no visible flame. It casts no flickering light that you could watch from a safe distance and recognize as combustion. It does not consume wood or oil or gas in any sense you would find familiar. It burns at temperatures so extreme that the very concept of temperature, a quantity we associate with warm rooms and hot ovens, and the comfortable heat of a summer afternoon becomes inadequate to describe what is happening, and it burns not at the surface of a thing, where fire normally lives, but at the absolute center, buried beneath layers of plasma, hundreds of millions of kilometers deep, in a place where no information about what is happening can reach the outside world in any timely way. This is the fire inside Stevenson 2-18, and it is going out. Not all at once. Not in the way a candle goes out when you pinch the wick. It is going out in stages, each stage shorter than the last, each stage burning a fuel that was itself the ash of the stage before it, each stage producing conditions more extreme and more desperate than anything the star has previously encountered in its long existence. The star has no awareness of this process. It has no mechanism for knowing that its core is approaching a state from which there is no recovery. Its enormous outer envelope, drifting and pulsing across a volume large enough to swallow the orbits of the inner planets, continues to behave exactly as it has for hundreds of thousands of years, shedding material, convecting energy upward through vast churning cells, glowing at 3,000 degrees in the infrared darkness of the galactic arm. The surface does not know what the core is doing. That disconnect between the placid, oblivious exterior and the accelerating crisis in the interior is one of the most disquieting things about how massive stars die. From outside, nothing changes. The star looks the same on the day its silicon ignites as it did a million years earlier. The light that leaves its photosphere carries no message about the countdown. The infrared glow that reaches our telescopes after 19,000 years of travel tells us nothing about the state of the nuclear burning happening at the star's center at the moment that light departed. We are, in every meaningful sense, blind to the most important thing happening inside the most extreme object in this region of the galaxy. But the physics does not care whether we are watching. The countdown began millions of years ago, at the moment the star first ignited hydrogen fusion in its core and took its place among the luminous blue giants that inhabit the upper reaches of the Hertzsprung-Russell diagram. At that point, the star was nothing like what it is today. It was compact, hot, brilliant, a blue supergiant radiating at temperatures exceeding 30,000 degrees, its surface gravity high, its envelope tightly bound, its radius perhaps 30 or 40 times that of our Sun rather than 2,000 times. It was a different kind of object entirely, violent and bright and consuming fuel at a rate that guaranteed its life would be brief by stellar standards. The hydrogen phase lasted several million years. Several million years sounds vast, and measured against a human lifetime, it is incomprehensible. The entirety of recorded human civilization spans roughly 5,000 years. The entirety of our species' existence on Earth spans perhaps 300,000 years. Several million years is 10 times the age of our species. It is longer than the time separating us from the common ancestor we share with chimpanzees. But measured against the lifetime of a sun-like star, several million years is nothing. Our Sun will spend approximately 10 billion years burning hydrogen in its core before the fuel is exhausted. Stevenson 2-18 burned through its hydrogen supply in a fraction of a percent of that time because the crushing weight of 25 to 30 solar masses pressing inward demanded core temperatures so extreme that the reaction rate was millions of times higher than in a smaller star. Massive stars do not live long lives. They live fast, extravagant lives, burning through their inheritance in a geological eye blink and leaving behind the most dramatic endpoints the universe produces. When the hydrogen was gone, the core contracted. Contraction heated the core. When the temperature climbed to roughly 100 million degrees Celsius, helium ignited. The star restructured around this new energy source. Its outer envelope expanded, its surface cooled, its color shifted from brilliant blue toward the deep red of a cool supergiant. The star became something recognizable as a predecessor to what Stevenson 2-18 is today, a bloated, luminous, extended object slowly converting the ash of hydrogen burning into the products of helium burning. The helium phase lasted a few 100,000 years. A few 100,000 years is the span of time separating us from the earliest anatomically modern humans. It is the time it would take light, traveling at 299,792 kilometers per second, to cross a distance of roughly 300,000 light years, 3 times the diameter of the Milky Way. It is an enormous span of time by any human measure, and it was over in a fraction of the time the hydrogen had lasted. This compression, each stage shorter than the last, by a factor that grows with each successive fuel, is not a coincidence. It reflects a fundamental physical reality about how nuclear binding energy changes as you move up the periodic table. Each heavier fuel releases less energy per unit mass when fused than the fuel before it. Helium fusion releases roughly 10 times less energy per kilogram than hydrogen fusion. Carbon fusion releases less than helium. Each successive stage must process fuel faster to maintain the outward pressure against gravity, which means each successive stage depletes its fuel more rapidly, which means the intervals between crises shrink with each step. The star is accelerating toward its end, not metaphorically, literally. The pace of change is increasing. When the helium was gone, the core contracted again. It heated again. Carbon ignited at temperatures approaching 500 million degrees Celsius. Carbon burning produced a mixture of neon, magnesium, and oxygen. It also produced something the earlier burning stages had not generated in significant quantities: neutrinos. At carbon-burning temperatures, thermal processes in the stellar plasma begin creating neutrino-antineutrino pairs directly from the energy of the plasma itself. These neutrinos, unlike photons, interact almost not at all with the surrounding stellar material. They pass through the star as though it were not there and carry their energy directly into space, bypassing the slow, diffusive process by which photons fight their way outward through millions of kilometers of plasma. This neutrino cooling accelerates the contraction of the core between burning stages, shortening the intervals still further. The star cannot stop the process from speeding up. Every mechanism that might slow the countdown instead hastens it. The carbon phase lasted a few thousand years. A few thousand years is the span of human recorded history. It is the time separating us from the construction of the Egyptian pyramids, from the first written legal codes, from the earliest cities built along the Tigris and Euphrates. It is long enough for languages to be born and die, for empires to rise and collapse, for entire civilizations to flourish and leave nothing behind but ruins and fragments. The carbon in Stevenson 2-18's core burned through all of it in the time it takes human civilization to go from stone tablets to smartphones. When the carbon was gone, neon ignited. The neon phase is unusual. It is driven not primarily by thermal fusion but by photodisintegration, a process in which high-energy gamma rays produced at the extreme temperatures of the late burning stages collide with neon nuclei and knock helium nuclei loose. These liberated helium nuclei then fuse with remaining neon to produce magnesium, releasing energy. The neon phase lasted approximately 1 year. 1 year, the time it takes Earth to complete a single orbit around the Sun. The time measured in seasons, in the cycle of a single agricultural year, in the span between 2 consecutive birthdays. Inside the core of a dying star, 25 times the mass of the Sun, an entire nuclear burning phase. The consumption of a fuel that took thousands of years to accumulate was complete in the time it takes a calendar to turn over once. Oxygen ignited next. At temperatures approaching 2 billion degrees Celsius, oxygen burning produced silicon, sulfur, phosphorus, and a cascade of isotopes through a complex network of nuclear reactions occurring simultaneously. The oxygen phase lasted a few months. A few months, a season, the time between the first frost of autumn and the last frost of spring, the time a pregnancy moves through its second trimester. In the core of Stevenson 2-18, an ocean of oxygen nuclei accumulated over millions of years of prior stellar evolution was exhausted in the time it takes a human body to gestate from conception to birth. And then finally, silicon. Silicon burning is the last act. It is the most complex and the most desperate of all the burning stages, driven by a web of photodisintegration and recapture reactions so intricate that astrophysicists describe it less as a single reaction and more as a statistical equilibrium, a nuclear quasi-equilibrium in which thousands of forward and reverse reactions occur simultaneously, and the overall trend is a slow rearrangement of nuclear matter toward the most stable configuration available. That most stable configuration is iron. Silicon burning lasts approximately 1 week. Sit with that. The final chapter of a nuclear burning sequence that began millions of years ago that has processed an amount of matter equivalent to several solar masses through a succession of fuels and temperatures and reaction networks of extraordinary complexity arrives at its conclusion in roughly 7 days. Not 7 years, not 7 centuries. 7 days, during which the silicon in the core is systematically converted into the iron peak elements, iron, nickel, cobalt, that represent the absolute terminus of nuclear energy release. During those 7 days, the outer envelope of Stevenson 2 to 18 continues to do exactly what it has been doing for hundreds of thousands of years. It pulses, it sheds material, it glows in the infrared. It convects enormous columns of plasma upward through its diffuse, tenuous layers in motions that take years to complete a single cycle. The star's surface has no more knowledge of the silicon burning in its core than the surface of the ocean has knowledge of tectonic processes occurring in the mantle thousands of kilometers below. The disconnection between the interior crisis and the exterior calm is absolute. This is the part that lodges in the mind and refuses to leave. While the most consequential nuclear process in the star's history, the process that will determine everything about how it dies, unfolds over 7 days in a sphere of iron the size of Earth at the star's center, the outer layers of the star continue their slow, oblivious performance across a volume large enough to swallow Saturn's orbit. The core and the envelope exist on completely different timescales. The core is counting down in days. The envelope is counting down in centuries. They are part of the same object, connected by gravity and radiation and convective energy transport, and yet they inhabit almost entirely separate physical realities. There is a detail here that deserves a moment of stillness. The neutrinos produced during the late burning stages, particularly the oxygen and silicon burning phases, are already leaving. They have been leaving for years. Every second, an enormous flux of neutrinos is streaming outward from the core of Stevenson 2 to 18, passing through the stellar envelope as though it were empty space, racing outward at effectively the speed of light, carrying energy away from the star into the surrounding galaxy. These neutrinos carry information about what is happening inside the core. They carry, encoded in their energies and flavors and emission rates, a complete record of the nuclear burning occurring at the star's center. But we cannot read them, not from Earth, not from 19,000 light-years away. The flux is too low, the distance too great, the signal too diffuse by the time it reaches our detectors. The neutrino observatories built underground around the world, Supergiant in Japan, Ice Cube in Antarctica, the Sudbury Neutrino Observatory in Canada, are sensitive enough to detect a burst of neutrinos from a nearby supernova. When supernova 1987A exploded in the Large Magellanic Cloud, 168,000 light-years away, 24 neutrinos were detected across multiple observatories in a pulse lasting 13 seconds. 24 particles, arriving from a dying star 168,000 light-years distant, were enough to confirm the fundamental physics of core collapse and earn a Nobel Prize. But 1987A was 168,000 light-years away. Stevenson 2 to 18 is 19,000 light-years away closer, but still far enough that the neutrino signal from its ongoing late burning stages, spread over years rather than seconds, is indistinguishable from background noise. We sit at our telescopes and our underground detectors, surrounded by the most sensitive instruments our civilization has produced, and the countdown occurring inside the largest star we have ever found proceeds in complete silence from our perspective. The iron core grows, day by day, layer by layer, silicon burning above it, raining iron ash downward, the core's temperature climbing, its density increasing. The electrons that have been providing additional support against gravity through a quantum mechanical effect called electron degeneracy pressure, being squeezed closer and closer to their theoretical limits. The Chandrasekhar limit is a number, 1.4 solar masses. At that mass, electron degeneracy pressure can no longer support the core against gravity under any conditions. Below that mass, it can. Above it, it cannot. The transition between these two states is not gradual. It is not a gentle crossing of a threshold. It is a cliff edge. And the iron core of Stevenson 2 to 18 is walking toward that edge, gram by gram, in the silence of a nuclear burning phase that will be complete before the next season changes. What happens at the moment it steps over that edge will be discussed in the next part of this story. But before we get there, it is worth sitting for one moment longer with the extraordinary nature of what we have just described. A star so vast that its outer layers have never felt any meaningful influence from its own core collapse. A star whose envelope drifts across a volume larger than the orbits of every inner planet contains. At its center, a sphere of iron the size of Earth, accumulating mass at a pace determined by nuclear physics that has no interest in the scale of the object surrounding it. The biggest thing we have ever found is dying from the inside out, and the inside does not know how big the outside is. Neither does the outside know how little time the inside has left. The collapse takes less time than it takes you to blink. Not metaphorically, not as a rhetorical device to suggest speed, in the most literal, measurable, physically precise sense available to us. The event that ends the life of a star, 25 times the mass of our Sun, the event that converts a core of iron the size of Earth into a sphere of neutrons 20 kilometers across, occurs in approximately 1/10 of a second. The human blink reflex takes between 100 and 400 milliseconds. Core collapse takes roughly 100 milliseconds. You could be in the middle of a blink when it happens, and the entire event would be over before your eyelids finish closing. In that 1/10 of a second, more energy is released than our Sun will radiate in its entire 10 billion year lifetime. Pause on that. Our Sun has been burning for approximately 4.6 billion years. It will burn for roughly another 5 billion years before it exhausts its hydrogen and expands into a red giant. Over that entire span, 10 billion years of continuous nuclear fusion, 10 billion years of light and heat pouring outward in all directions at the rate of approximately 3.8 times 10 to the 26th watts. The total energy our Sun will ever produce across its complete existence can be calculated. It is an enormous number. It is the number responsible for every photon that has ever warmed a living thing on Earth, every joule that has ever driven weather or ocean currents or the chemistry of photosynthesis, every unit of energy that has sustained the only known biosphere in the universe across nearly 4 billion years of continuous life. The core collapse of Stevenson 2 to 18 releases that same quantity of energy in 1/10 of a second. This is not an approximation. It is not an order of magnitude estimate designed to sound impressive. It is the actual physics of what happens when a mass greater than our Sun falls inward from the size of Earth to the size of a city in the time it takes a nerve impulse to travel from your fingertip to your brain. Gravitational potential energy of that magnitude, released on that timescale, produces an energy output so extreme that it dwarfs every other astrophysical process except the Big Bang itself. A core collapse supernova is not merely a large explosion, it is a different category of event, one that operates at energy scales for which human language has no adequate vocabulary. But before the explosion, there is a moment of stillness. To understand what happens in the last second of this star's core, you need to understand what electron degeneracy pressure is and why it fails at the Chandrasekhar limit. Throughout the late burning stages, the iron core has been supported against gravity not only by thermal pressure, the outward push of hot plasma, but by a quantum mechanical effect rooted in one of the fundamental principles of nature. Electrons, like all particles classified as fermions, obey the Pauli exclusion principle. No two electrons can occupy the same quantum state simultaneously. As the core is compressed to ever higher densities, electrons are forced into closer and closer proximity. The exclusion principle resists this compression with a pressure that does not depend on temperature. It exists even at absolute zero, a consequence of quantum mechanics rather than thermodynamics. This electron degeneracy pressure is what supports white dwarf stars, the remnants of sun-like stars that have exhausted their nuclear fuel. A white dwarf, the mass of our sun, maintains its structure indefinitely against gravity through electron degeneracy pressure alone, with no ongoing nuclear burning required. It simply sits there, a sphere roughly the size of Earth, slowly cooling over billions of years, its electrons locked in their quantum states, resisting compression. But Chandrasekhar showed that this support has a limit. As the mass of the core approaches 1.4 solar masses, the electrons required to maintain degeneracy pressure must move at velocities approaching the speed of light. At that point, relativistic effects reduce the effectiveness of the pressure faster than the density increases. The support becomes insufficient. Above this mass, no amount of electron degeneracy pressure can hold the core against gravity. When the iron core of Stevenson 2-18 crosses this threshold, something happens that has no analog in ordinary experience. The core does not begin to collapse slowly and accelerate. It does not sag gradually inward like a building whose foundation is weakening. The transition from supported to unsupported is nearly instantaneous, and the collapse that follows is essentially freefall matter, falling inward under gravity, with almost nothing to slow it down. The outer edge of the iron core, roughly the size of Earth moments before collapse, falls inward at roughly 1/4 the speed of light. In the first few milliseconds, the core shrinks from the size of Earth to the size of a large city. The density climbs past the density of an atomic nucleus, roughly 2.3 times 10 to the 14th grams per cubic centimeter, a density at which a single teaspoon of material weighs approximately 1 billion tons. At this density, the individual atomic nuclei that composed the iron core dissolve. Protons and neutrons are packed together as tightly as the strong nuclear force allows, squeezed so close that they form a single macroscopic quantum object, a neutron star in the process of being born. And at this point, something extraordinary happens. The collapse stops, not because gravity has been overcome, not because some new energy source has ignited, but because nuclear matter, compressed to its maximum possible density, becomes essentially incompressible. The strong nuclear force, which binds protons and neutrons together inside nuclei, also resists compression beyond a certain density. When the infalling core material reaches nuclear density, it encounters this resistance, and the collapse abruptly halts. The inner core bounces. This bounce sends a shock wave outward through the still infalling outer layers of the core. The shock wave is, in the first instant, moving outward against a tide of material still falling inward at 1/4 the speed of light. It stalls almost immediately, losing energy. As it dissociates the iron nuclei, it passes through a process that absorbs energy rather than releasing it, robbing the shock of its momentum. For a fraction of a second, the situation is precarious. The shock has stalled. The outer core is still falling inward. If nothing else happened, the collapse might continue past the neutron star phase entirely, forming a black hole without any outward explosion, the star simply swallowing itself in silence, leaving no visible supernova at all. But something else happens. Neutrinos. In the extreme conditions of the proto-neutron star, temperatures of tens of billions of degrees, densities exceeding nuclear density, the processes that produce neutrinos operate at rates that dwarf anything in the earlier burning stages. The proto-neutron star radiates neutrinos with an intensity that is almost impossible to state coherently. In the first 10 seconds following core bounce, the nascent neutron star emits approximately 3 times 10 to the 53rd joules of energy in the form of neutrinos. This is 99% of the total energy released by the entire supernova. The visible light of the explosion, the brilliant display that briefly rivals the combined output of 100 billion stars, represents roughly 1% of the total energy budget. The neutrinos carry away the binding energy of the neutron star. They are produced in enormous quantities by the capture of electrons onto protons, by thermal pair production in the extreme plasma, by a dozen other processes that operate only at these densities and temperatures. They stream outward from the proto-neutron star at effectively the speed of light. But unlike in the normal stellar interior, where neutrinos pass through matter without interaction, the densities in the collapsing core are high enough that even neutrinos are temporarily trapped. For the first 100 milliseconds or so, the neutrino luminosity is held in check by the opacity of the dense nuclear matter. Then, as the density falls off with distance from the center, the neutrinos decouple from the matter and stream freely outward. A small fraction, roughly 1% of these neutrinos deposit their energy in the stalled shock wave. 1% of 10 to the 53rd joules is 10 to the 51 joules. This is the energy that revives the shock, not through any exotic mechanism, not through any process that violates known physics. Simply through the sheer overwhelming scale of the neutrino luminosity, so enormous that even a tiny fraction of it, absorbed by the matter behind the stalled shock, is sufficient to push the shock outward again with enough energy to blow apart the entire stellar envelope. The revived shock accelerates outward through the layers of the star above the core. It encounters the silicon-rich layers above the iron core and blasts through them. It encounters the oxygen-rich layers and blasts through them. The neon layers, the carbon layers, the helium shell, the enormous hydrogen envelope that makes up most of the star's mass by volume. The shock races through all of it at velocities of roughly 10,000 to 30,000 kilometers per second. Now consider what that means for Stevenson 2 to 18 specifically. The shock wave must cross the entire radius of this star, not the radius of a typical supergiant, which might be 500 or 1,000 solar radii. The estimated radius of Stevenson 2 to 18 is 2,150 solar radii, approximately 1.5 billion kilometers. The shock wave, traveling at 20,000 kilometers per second, will take approximately 75,000 seconds to cross the full radius of the star. That is roughly 20 hours. 20 hours for the explosion to reach the surface. For 20 hours after the core collapses, the outer layers of Stevenson 2 to 18 will have no indication that anything has changed. The photosphere will continue to glow. The circumstellar dust will continue to absorb and re-radiate energy. The stellar wind will continue to push material outward into the surrounding space. The outer envelope will continue its slow, oblivious pulsation. Then the shock arrives. When the shock wave reaches the photosphere of this star, the event is called shock breakout. It is one of the most intense bursts of radiation in the observable universe. Brief, but extraordinarily luminous. A flash of ultraviolet and X-ray radiation produced as the shock wave heats the photospheric material from thousands of degrees to millions of degrees in a matter of minutes. For Stevenson 2 to 18, whose photosphere spans a surface area roughly 2,150 squared, more than 4.5 million times the surface area of the Sun, the shock breakout will be among the most energetic ever produced by a star of the type. The flash lasts minutes to hours, then it gives way to something more sustained. The explosion that follows shock breakout is what astronomers call the supernova plateau, a period lasting weeks to months during which the expanding ejector remains hot and luminous, powered partly by the radioactive decay of nickel 5-6 produced in the explosion into cobalt 5-6 and then into iron 5-6. During this phase, the supernova can briefly outshine the entire galaxy that contains it. If Stevenson 2 to 18 were close enough, within a few thousand light-years rather than 19,000, it would be visible in daylight, a second sun in the sky, casting shadows at night, remaining visible to the naked eye for months. At 19,000 light-years, it will be visible to the naked eye as a new bright star, probably comparable in brightness to Venus or Jupiter at their most luminous. It will appear in the constellation Scuti, a fixed point of extraordinary brightness that was not there before, and it will remain visible for months before slowly fading as the ejector expands and cools. The total kinetic energy of the expelled material, the actual mechanical energy of all the mass being thrown outward at tens of thousands of kilometers per second, is approximately 10 to the 44 joules. This is the energy that will disperse the star's envelope across hundreds of light-years of interstellar space over the following thousands of years, creating a supernova remnant that will be detectable to radio and X-ray telescopes for tens of thousands of years after the initial explosion. For perspective, 10 to the 44 joules is roughly the total energy output of our Sun over 3 million years. The kinetic energy of the explosion alone, not the neutrinos, not the light, just the mechanical energy of the matter being thrown outward, equals everything our Sun will radiate across a span 3 times longer than the entire existence of our species. And the material being thrown outward is not simply the hydrogen and helium of the outer envelope. It is a record of everything the star has ever been. The outer layers carry the hydrogen and helium present since the star's formation. Deeper layers carry the carbon and oxygen synthesized during helium burning. Deeper still, neon, magnesium, silicon, sulfur, the products of each successive burning stage, preserved in concentric shells like the rings of a tree, now all blasted outward simultaneously into the surrounding interstellar medium. And in the innermost layers of the ejecta, in the material that was once silicon and is now iron and nickel and cobalt, and in the extraordinary conditions at the shock front itself, where neutron capture processes can build elements heavier than iron that no stellar burning stage can produce, are the seeds of everything that comes next. Gold, silver, platinum, strontium, barium, the heavy elements that exist nowhere else in the universe except in the immediate aftermath of events like this one. Every piece of gold jewelry ever worn by a human being, every platinum catalyst in every catalytic converter ever installed in a vehicle, every silver contact in every electrical circuit, all of it traceable, atom by atom, to the explosive deaths of massive stars, to events identical in physics to the one that awaits Stevenson 2 to 18. The shock wave reaches the surface. The envelope detonates. The star that took millions of years to build, that spent hundreds of thousands of years as the largest known stellar object in the galaxy, is gone in less than a day. What remains at the center, if the core mass falls within the right range, is a neutron star, a sphere 20 kilometers across containing more than a solar mass of matter, spinning perhaps hundreds of times per second, radiating beams of radio waves from its magnetic poles like a lighthouse in the dark. Or, if the core mass is high enough, the neutron star itself collapses further, and what remains is a black hole, a region of space-time from which not even light can escape, a gravitational wound in the fabric of the universe, sitting at the center of an expanding cloud of stellar debris. Either way, the largest star we have ever found will have become the smallest thing imaginable. Everything it ever was, scattered. Everything it never was, just beginning. After the light fades, the silence returns. Not immediately. For weeks, the expanding shell of ejected material continues to glow, powered by the radioactive decay of nickel and cobalt produced in the explosion, sustained by the collision of the outward-moving ejecta with the circumstellar material that Stevenson 2 to 18 spent hundreds of thousands of years shedding into the surrounding space. The supernova remnant brightens, peaks, and then begins the long, slow decline that all supernovae follow as their ejecta expands and cools, and the energy sources driving their luminosity exhaust themselves one by one. Months pass, the light curve drops. The new star in Scutum that briefly rivaled Venus fades to the threshold of naked eye visibility, then below it, then into invisibility. The event that was, for a few weeks, the most luminous object in this region of the galaxy becomes a faint smear, detectable only to sensitive infrared and radio telescopes. The show, from the perspective of any observer watching from Earth, is over, but the remnant is just beginning. What the explosion leaves behind exists on two scales so different from each other that describing them in the same breath requires a conscious effort to hold both in mind simultaneously. At the center, compressed into a volume that makes the word small inadequate, is the collapsed core, a remnant whose physical properties are so extreme that they challenge the foundations of the physics used to describe them. Surrounding it, expanding outward at tens of thousands of kilometers per second, is the ejecta, several solar masses of stellar material flung into the interstellar medium, carrying within it every element the star ever synthesized across millions of years of nuclear burning. The center first, when the iron core of Stevenson 2 to 18 collapsed and bounced. The inner portion of the core, the region that reached nuclear density and became incompressible, did not rebound outward with the shockwave. It stayed behind. It is the neutron star, or what will become one, sitting at the origin point of the explosion while the rest of the star is blown away around it. A neutron star is not merely a very dense star. It is a qualitatively different kind of object, one that cannot be understood through any analogy drawn from ordinary matter. Its density is not simply high, it is the highest density at which matter, as we understand matter, can exist without collapsing further. A sphere 20 kilometers in diameter, containing 1.4 times the mass of our Sun, a teaspoon of its material weighing 1 billion tons. Its surface gravity, roughly 200 billion times the surface gravity of Earth. Its escape velocity at the surface approximately half the speed of light. To stand on the surface of a neutron star, a thought experiment with no practical possibility of execution, would require surviving a gravitational field so intense that it would compress you to a layer thinner than an atomic nucleus before you arrived. The tidal forces across the length of a human body in a gravitational field that strong would exceed the electromagnetic forces holding your atoms together. You would not land on the surface. You would become part of it, indistinguishable from the surrounding material in a fraction of a millisecond. The interior of a neutron star is one of the least understood environments in physics. Near the surface, the material is thought to consist of a crystalline lattice of neutron-rich atomic nuclei, iron, and heavier elements compressed beyond their normal structural limits, but retaining some semblance of nuclear identity. Deeper inside, as the density climbs toward and beyond nuclear density, individual nuclei dissolve into a sea of free neutrons, protons, and electrons, with the neutrons dominating. Still deeper, in the innermost regions where the density exceeds anything reproducible in terrestrial laboratories, the behavior of matter is genuinely unknown. Theoretical proposals include exotic states such as quark matter, a phase in which the quarks that normally compose protons and neutrons are freed from confinement and flow as a collective and strange matter, involving quarks of the strange flavor that do not appear in ordinary nuclei. These proposals are not confirmed. The instruments needed to probe the interiors of neutron stars do not yet exist, and may never exist. What we know comes from the outside, from measurements of neutron star masses and radii, using X-ray and gravitational wave observations, from the timing of pulsar signals, from the brief electromagnetic counterparts of neutron star mergers detected since the landmark event of August 2017. What lies at the center of a neutron star remains, in the most honest, scientific sense, unknown. What we do know is this. When a neutron star forms in the collapse of a massive star, it inherits the angular momentum of the collapsing core. Angular momentum is conserved as the core shrinks from the size of Earth to the size of a city. Any rotation it possessed is amplified enormously, the way a spinning ice skater accelerates when pulling their arms inward. A core rotating even slowly before collapse will emerge as a neutron star spinning at extraordinary rates. Newly formed neutron stars have been observed spinning hundreds of times per second. Some spin at nearly 1,000 revolutions per second, so fast that material at the equator is moving at a significant fraction of the speed of light. The magnetic field is amplified by the same process. The magnetic field of the collapsing core, compressed into a sphere 20 kilometers across, emerges as a field of extraordinary strength, typically 10 to the 12 Gauss, roughly 1 trillion times the strength of Earth's magnetic field. This field, combined with the rapid rotation, creates conditions for one of the most precise natural clocks in the universe. Charged particles accelerated along the magnetic poles emit beams of radiation, radio waves, sometimes X-rays that sweep through space with every rotation. If one of these beams is oriented toward Earth, we detect it as a pulsar, a rhythmic series of radio pulses arriving with a regularity that rivals atomic clocks. If Stevenson 2-18 produces a neutron star, and if that neutron star's beam sweeps past Earth, the pulsar will be detectable for millions of years, gradually slowing as it loses rotational energy to electromagnetic radiation, eventually fading into an unremarkable, cold, dark sphere, drifting through the remnant of the explosion that created it. But the neutron star is not guaranteed. The mass of the collapsing core determines which path the remnant takes. If the core mass after the explosion falls below approximately 2 to 3 solar masses, the theoretical maximum mass a neutron star can support against gravity through neutron degeneracy pressure and the strong nuclear force, a neutron star forms and survives. If the core mass exceeds this threshold, the neutron star itself becomes unstable. Gravity overcomes even the resistance of nuclear matter. The collapse continues past nuclear density, past any known state of matter, into a singularity. A black hole forms. The threshold between neutron star and black hole formation is not precisely known. It depends on the equation of state of nuclear matter at extreme densities, the relationship between pressure and density in a regime that terrestrial physics cannot directly probe. Estimates from theoretical modeling and gravitational wave observations of neutron star mergers suggest the maximum neutron star mass lies somewhere between 2 and 3 solar masses, but the exact value remains uncertain. For a star as massive as Stevenson 2 to 18, the probability of black hole formation is not negligible. Massive stars can produce black holes either through direct collapse if the shock wave fails to revive and the entire star falls inward without a visible supernova, or through fallback, in which the initial explosion succeeds, but a significant fraction of the ejector falls back onto the proto-neutron star, accumulating mass until the neutron star crosses the stability threshold and collapses further. A black hole formed this way carries none of the drama associated with the supernova itself. It does not announce its existence with a flash of light or a burst of radio waves. It simply sits at the center of the expanding remnant, a region of space-time from which escape is impossible, its presence betrayable only through its gravitational influence on surrounding matter, or through the Hawking radiation. It theoretically emits a radiation so faint at stellar black hole masses that it will never be directly detected by any instrument humanity could conceivably build. The boundary of a black hole, the event horizon, is not a physical surface. It is a geometric boundary, the distance from the center at which the escape velocity equals the speed of light. For a black hole of 3 solar masses, this boundary lies at a radius of roughly 9 kilometers. Inside it, the laws of physics as we understand them break down. General relativity predicts a singularity, a point of infinite density at the center, but most physicists regard the singularity as a marker of the theory's incompleteness rather than a genuine physical object. What actually exists at the center of a black hole is one of the deepest open questions in fundamental physics. From outside, the black hole is simply an absence, a region where the light from behind it is bent around it, where matter falling in is compressed and heated and radiates intensely before crossing the event horizon, where gravitational waves are emitted if a companion object spirals inward. The explosion that created it is long over. The light has faded. The neutron star that might have existed briefly before the fallback mass crossed the stability threshold is gone. At the center of the expanding remnant of the largest star we have ever found, there may be nothing detectable at all, but the remnant itself, the expanding shell of ejected material, is anything but nothing. Several solar masses of gas and dust are moving outward at tens of thousands of kilometers per second. In the first years after the explosion, the ejector is dense enough to be opaque, a hot, glowing shell that produces the visible supernova light. As years become decades and decades become centuries, the shell expands and thins. It becomes transparent. It begins to interact with the interstellar medium surrounding it, sweeping up ambient gas and forming a shock wave at its leading edge that accelerates interstellar particles to high energies. After 1,000 years, the remnant is a sphere several light years across, glowing in X-rays and radio waves as the hot ejector slams into the surrounding medium. After 10,000 years, it has expanded to tens of light years across, a diffuse bubble of hot gas, slowly dissipating into the surrounding interstellar medium. After 100,000 years, it has merged with the ambient gas of the Scutum Centaurus arm, its boundaries indistinguishable from the surrounding material. But the elements it carries do not disappear. This is the part of the story that connects the death of a star to everything that came after it, including you. The ejecta of a core collapse supernova is not simply the original stellar material, unchanged. The explosion itself is a site of nucleosynthesis, nuclear reactions driven by the extraordinary conditions of the shock wave and the neutron-rich environment near the collapsed core produce elements that could not be created in any prior burning stage. The rapid neutron capture process, called the R process, occurs in the extreme neutron flux near the proto-neutron star during the first seconds of the explosion. In this environment, atomic nuclei capture neutrons faster than they can decay, building up neutron-rich isotopes of heavy elements in a chain that reaches far beyond iron on the periodic table. Gold, platinum, lead, uranium, the heaviest naturally occurring elements in the universe, are synthesized in environments like the one that exists for a few seconds at the center of a core collapse supernova and in the mergers of neutron stars that were themselves products of prior supernovae. Every atom of gold that has ever existed on Earth was created in an event of this kind, an explosion or a collision somewhere in the history of the galaxy, long before the solar system formed. The iron in your blood was forged in the cores of massive stars and released into the interstellar medium by supernovae, like the one awaiting Stevenson 2-18. The calcium in your bones was produced in silicon-burning shells and scattered by explosion. The oxygen in every breath you take was synthesized in helium-burning and neon-burning and oxygen-burning stages in stars that lived and died billions of years before Earth existed. The carbon that forms the backbone of every organic molecule in your body was produced in the triple alpha process, in which 3 helium nuclei fuse to form a carbon nucleus in the cores of evolved stars. You are not made of star stuff in a poetic sense. You are made of star stuff in a literal, traceable, nuclear physics sense. The atoms composing your body were forged in stellar interiors and delivered to the interstellar medium by stellar explosions. They drifted through space for billions of years, accumulated into the molecular cloud that collapsed to form the solar system, and eventually found their way into the chemistry of a planet and then into the chemistry of life. The supernova remnant of Stevenson 2-18, when it finally disperses into the interstellar medium of the Scutum Centaurus arm, will seed that region of the galaxy with the products of millions of years of stellar nucleosynthesis. Some fraction of that material will, over billions of years, find its way into new stars and new planetary systems. Some fraction of those planetary systems may, under the right conditions, develop chemistry complex enough to produce something that wonders about the process that created it. The death of the biggest star we have ever found is not an ending. It is a dispersal, a redistribution, a slow return of borrowed matter to the medium from which it came, enriched by everything the star learned to build during its brief, extravagant existence. The remnant expands, the elements scatter. The darkness that follows is not empty. It is full of what comes next. Consider a single photon. It was born in violence. In the first moments after the shock wave of a supernova broke through the surface of a star larger than Saturn's orbit, the photosphere of that star was heated from 3,000 degrees to several million degrees in a matter of minutes. The thermal energy of that heating produced radiation across the entire electromagnetic spectrum: X-rays, ultraviolet, visible light in a burst so intense and so brief that astronomers call it shock breakout and regard it as one of the most luminous transient events a star can produce. In that burst, among the uncountable photons released, one particular photon was emitted in the direction of a small, unremarkable yellow star sitting in one of the outer spiral arms of the same galaxy. The photon left the dying star's surface at the speed of light, 299,792 kilometers per second, and began a journey that would take 19,000 years to complete. It is possible that this photon has already been traveling for some time. It is possible it has not yet been created. We do not know. And that uncertainty, the simple, irreducible fact that we cannot determine whether Stevenson 2-18 has already exploded or is still burning, is one of the most disquieting features of doing astronomy across cosmological distances. We observe the universe not as it is, but as it was. Every telescope is a time machine pointed backward. Every photon that reaches our detectors carries information about the state of its source at the moment of emission, which may be separated from the present moment by thousands or millions or billions of years. We have no way to observe the present state of anything beyond our immediate cosmic neighborhood. The universe is too large, and light is too slow for simultaneity to have any practical meaning at these distances. So we must work with what we have. Stevenson 2-18 is approximately 19,000 light-years from Earth. The light we observe from it tonight, if observe is even the right word, for detecting infrared radiation from a dust-obscured object invisible to the naked eye, departed the star approximately 19,000 years ago. This means we are currently observing Stevenson 2-18 as it existed around the year 17,000 BCE, give or take the substantial uncertainty in the distance measurement. The year 17,000 BCE. To feel what that means, you need to place it in human time. In 17,000 BCE, the most recent ice age was approaching its maximum extent. Ice sheets covered much of northern Europe and North America, extending as far south as what is now the northern United States. Sea levels were roughly 120 meters lower than today, exposing land bridges that connected continents now separated by ocean. The population of the entire planet was perhaps 5 million people fewer than live in a single modern city, scattered across Africa, Asia, Europe, and Australia, in small groups of hunter-gatherers who had not yet developed agriculture, writing, permanent settlement, or any of the technologies that define what we call civilization. The light we are receiving now from Stevenson 2-18 left that star when those people were alive, when they were hunting megafauna on frozen plains, painting animals on cave walls by firelight, following herds across landscapes that no longer exist. The photons that reach our infrared telescopes tonight have been traveling since before the invention of the wheel, before the first city, before the first written word, before every civilization whose name you have ever learned in school had drawn its first breath. This is the baseline. This is what we can say with confidence about the light we are currently receiving. What we cannot say is what Stevenson 2-18 is doing right now at this moment, in the present, as you read these words. The star's current state is, in the most precise sense, unknowable to us. The information about its present condition will not arrive for another 19,000 years. Whatever is happening in its iron core at this moment, whether the Chandrasekhar limit has been reached, whether collapse has already begun, whether the shock wave is already racing outward through its envelope, that information is sealed inside a sphere of light, expanding outward from the star. And the leading edge of that sphere is currently somewhere between the star and Earth, unreachable until it arrives. So let us do the calculation. Let us ask, specifically and concretely, when the light from the death of Stevenson 2-18 will reach Earth, under different assumptions about when the explosion occurs. If Stevenson 2-18 explodes tonight, if the iron core crosses the Chandrasekhar limit at this very moment, and the collapse begins, the light from the explosion will reach Earth in approximately 19,000 in years. The year will be roughly 21,026 CE. The human civilization that witnesses the new star appearing in Scutum will be separated from us by a gulf of time equal to the distance between us and the people who painted the caves at Lascaux. Whatever that civilization looks like, whatever languages it speaks, whatever understanding of the universe it has developed, it will observe the death of Stevenson 2-18 and know nothing of the people who first measured it, named it, and wondered when it would end. If Stevenson 2-18 exploded 1,000 years ago, in roughly 1025 CE, when Viking settlements dotted the North Atlantic coast of North America and the Song dynasty was at its height in China, the light will arrive in approximately 18,000 years, around the year 20,000 CE. A civilization 18,000 years more advanced than ours will be the first to see it. If the explosion occurred 5,000 years ago, around 3000 BCE, when the first writing systems were being developed in Mesopotamia and Egypt, when Stonehenge was under construction on the Salisbury Plain, when the wheel was new, the light will arrive in roughly 14,000 years. If it exploded 10,000 years ago at the dawn of the Neolithic Revolution, when human beings were just beginning to cultivate crops and domesticate animals, when the transition from nomadic hunter-gatherer existence to settled agricultural life was occurring independently in multiple regions of the world, the light arrives in roughly 9,000 years. None of these scenarios will be witnessed by anyone alive today. None will be witnessed by anyone whose existence we can meaningfully imagine from where we stand. The shortest plausible interval between the explosion and the arrival of its light at Earth is still measured in thousands of years, a span of time that encompasses the entirety of recorded human history multiple times over. We will not see it. This is not a limitation of our technology or our intelligence or our determination. It is a consequence of the size of the universe and the finite speed of light, two facts that combine to ensure that the most distant objects we can observe are observed only in their past states, and that the consequences of events occurring at those distances will not reach us within any time frame relevant to our lives or our civilization as it currently exists. But the light is traveling. Right now, if Stevenson 2-18 has already exploded, and the probability is not negligible, given that the star's current evolutionary state suggests it is within the last few percent of its nuclear burning lifetime, a sphere of light is expanding outward from the explosion site at 299,792 kilometers per second. This sphere is enormous. After 10,000 years of travel, it has a radius of 10,000 light-years and a surface area of roughly 1.26 times 10 to the 9th square light-years. It is sweeping through the interstellar medium of the Scutum Centaurus arm, encountering gas clouds and dust lanes and other stars, some of which may harbor planets, some of which may harbor something that notices the sudden brightening of a nearby star and wonders what it means. The leading edge of this sphere, if the explosion occurred 10,000 years ago, is currently somewhere approximately 9,000 light-years from Earth, roughly halfway through its journey. It is passing through regions of the galaxy that we can observe but not interact with, crossing volumes of space that contain millions of stars and unknown numbers of planetary systems. It carries within it the information of the explosion, the spectrum of the expanding ejector, the light curve of the fading fireball, the X-ray signature of the shock wave, the neutrino burst that preceded it by hours. All of this information, encoded in photons of every wavelength, racing outward in all directions at the same speed. The neutrinos, it should be noted, are already here. Neutrinos from the collapse, if it has occurred, travel at effectively the speed of light negligibly slower, by fractions that are immeasurable with current technology. They passed through Earth hours before the first light of the explosion could reach us. If the explosion has already happened, they passed through your body. They passed through the Earth itself, through rock and ocean and atmosphere, without interacting with a single atom, billions of them carrying information about the death of the largest star in the galaxy, streaming through everything you have ever touched, leaving no trace. We did not detect them. Our neutrino observatories are not sensitive enough to register the diffuse background flux from a distant supernova in an ongoing burning stage and a burst neutrino signal from 19,000 light-years away. If it has already arrived, would have been a handful of events spread over such a long baseline that they would be indistinguishable from background noise. The death of Stevenson 2-18, if it has already occurred, announced itself to Earth in a language we cannot yet read, through detectors we do not yet have, and we missed it entirely. What we will not miss, when the optical signal finally arrives, is the light. A supernova at 19,000 light-years will reach an apparent visual magnitude of roughly -6 to -8 at peak brightness, comparable to or somewhat brighter than Venus at its most luminous, easily visible in daylight, casting faint shadows at night, remaining visible to the naked eye for weeks or months. It will appear as a new star in Scutum, a constellation not particularly prominent in the night sky, suddenly hosting a point of light that outshines everything around it. Amateur astronomers will notice it within hours of its appearance. Professional observatories will pivot immediately. The world will know, and the world that knows it will not know our names. The civilization that witnesses the death of Stevenson 2-18 will be separated from us by an interval equal to the entire span of recorded human history, multiplied by a factor of at least 3. The languages we speak will be as incomprehensible to them as the proto-languages of the Neolithic are to us. The records we keep, the databases, the papers, the videos, the servers will have benchen fimesos, benchen flusing paftro, ventral scales of technological change and cultural transformation. If anything of what we know survives to that moment, it will survive the way the cave paintings at Lascaux survive, not as living knowledge, but as archaeological artifact, a trace of creatures who looked at the same sky and wondered about the same lights and left behind what evidence they could of the fact that they had noticed. They noticed. That is what all of this is. A species noticing, a civilization pointing its instruments at a patch of dusty sky in Scutum and extracting from the faint infrared signal of an obscured giant star enough information to calculate its distance, estimate its size, model its internal structure, predict its fate, and understand the physics that connects its death to the atoms composing the body of the person reading these words. We will not see the explosion, but we saw the star. We measured it, argued about its size, debated its cluster membership, modeled its circumstellar dust, detected its maser emissions, calculated its mass loss rate, and understood that it was dying. We did all of this from 19,000 light-years away, using instruments built in a few centuries by a species that has existed for a few 100,000 years, on a planet orbiting an unremarkable star in an outer spiral arm of an average galaxy. The light from the death of Stevenson 2-18 is either already traveling toward us or has not yet begun its journey. Either way, it is coming, and it does not know we are waiting. There is a question underneath all of this that has not yet been asked directly. Not the question of how large Stevenson 2-18 is, though that question opened this story. Not the question of when it will die, though that question has occupied the last several thousand words. Not even the question of what will remain after the explosion, or when the light will arrive, or who will be alive to see it. Those questions are important. They are the scaffolding of the story. But the question underneath them, the one that gives all the others their weight, is simpler and more personal than any of them. What does any of this have to do with you? Not with humanity in the abstract, not with civilization as a concept, or science as an enterprise. With you, specifically. The person reading these words right now, in whatever room or vehicle or corner of the world you currently occupy, breathing air, feeling the weight of your own body, aware in some peripheral way of the warmth of your own existence against the background of everything this story has described. The answer is not metaphorical. It is chemical. It is nuclear. It is written in the composition of your own body at the level of individual atoms, and it connects you to events that occurred before the Earth existed, in deaths more violent than anything in the observable history of this planet, across distances that make the 19,000 light-years separating us from Stevenson 2-18 seem modest by comparison. You already know the broad outline. Every science communicator, every educator, every documentary has told some version of it. You are made of stardust. The atoms in your body were forged in stars. Carl Sagan said it. Neil deGrasse Tyson says it. It has been printed on posters and embroidered on cushions and repeated so many times that it has acquired the smooth, frictionless quality of a phrase that has lost contact with its own meaning. So let us restore the friction. Let us be specific. Let us trace the atoms in your body, not to stars in general, not to the comforting abstraction of cosmic ancestry, but to the specific physical processes that created them, processes identical in their physics to the ones described in this story. Because the comfort of the familiar version of this idea hides something that is, when you look at it directly, genuinely vertiginous. Start with the iron in your blood. Your body contains approximately 4 grams of iron, distributed primarily in the hemoglobin molecules of your red blood cells. These molecules use iron atoms to bind oxygen and carry it from your lungs to every tissue in your body. Without this iron, the oxygen transport system that sustains your existence fails within minutes. The iron is not optional. It is not decorative. It is structural, functional, irreplaceable. Where did it come from? Not from the Earth's crust, where iron is abundant. In any ultimate sense, the iron in the Earth's crust was there when the planet formed, condensed from the solar nebula 4.6 billion years ago. The solar nebula, the cloud of gas and dust from which the Sun and all the planets were assembled, contained iron because the galaxy's interstellar medium contained iron. The interstellar medium contained iron because, over the preceding billions of years, generations of massive stars had lived and died, synthesizing iron in their cores through the exact sequence of burning stages described in this story, and dispersing it into the surrounding galaxy through the exact type of core collapse supernova that awaits Stevenson 2 to 18. The iron in your blood was made in the core of a dying star. Not poetically, not as a figure of speech. The specific iron, 5-6 nuclei, that your hemoglobin uses to carry oxygen were assembled, proton by proton and neutron by neutron, inside the silicon-burning core of a massive star that exhausted its nuclear fuel, collapsed, and exploded sometime in the first several billion years of the galaxy's history. The energy released in that collapse scattered those iron nuclei into the interstellar medium. They drifted through space for millions or billions of years. They were swept up in the collapse of the molecular cloud that formed the solar system. They condensed into the rocky material of the early Earth. They were processed through geological cycles, dissolved into the oceans, incorporated into the chemistry of early life, passed from organism to organism through billions of years of biological evolution, and eventually arrived in you. Every red blood cell in your body carries iron atoms with a history longer than the Earth itself. Now, consider the calcium in your bones. Your skeleton contains approximately 1 kilogram of calcium, providing the structural rigidity that allows you to stand, move, and exist as a solid object rather than a formless mass. Calcium is synthesized in the oxygen-burning and silicon-burning stages of massive stellar evolution, the same stages described in this story as the penultimate chapters of Stevenson 2 to 18's countdown. It is dispersed into the interstellar medium by supernova explosions identical to the one this star is approaching. It followed the same journey as the iron interstellar medium to solar nebula, to Earth, to geology, to biology, to you. The skeleton that holds you upright was assembled from the ash of dying stars. The oxygen in every breath. You take the element that constitutes roughly 21% of Earth's atmosphere, and that your cells use to extract energy from food through the same basic chemical logic that a fire uses. To extract energy from wood was synthesized in helium burning and neon burning stages in massive stars. It was scattered by supernovae. It became part of the Earth's early atmosphere through volcanic outgassing and the chemistry of the young planet. It was transformed by billions of years of photosynthesis from carbon dioxide into free molecular oxygen. And now, every few seconds, you draw it into your lungs and use it to sustain the process that makes you alive. The carbon that forms the backbone of every organic molecule in your body, every protein, every lipid, every nucleic acid, every sugar, was synthesized in the triple alpha process, in which 3 helium nuclei fuse to form a carbon, 1,2 nucleus in the cores of evolved stars. This process was understood theoretically only after Fred Hoyle, the British astrophysicist, predicted in 1954 that carbon, 1,2, must have an excited nuclear energy state at a specific energy level. Otherwise, the triple alpha process would be too slow to account for the abundance of carbon in the universe. The state was found experimentally within months of Hoyle's prediction. It is sometimes called the Hoyle state, and its existence is the reason carbon-based life is possible. Without it, the carbon that makes you a carbon-based organism would be vanishingly rare in the universe. The fact that you are carbon-based is a consequence of nuclear physics. The fact that nuclear physics has the specific properties it has is a fact about the universe that we observe but cannot yet explain. The universe is arranged at the level of fundamental constants and nuclear energy levels in a way that makes carbon abundant, and carbon abundance is what makes you possible. This is not a comfortable thought. It is a vertiginous one. You are not a visitor to the universe, passing through a cosmos that existed before you and will continue after you. You are a temporary local configuration of matter that the universe has been assembling for billions of years, through processes of unimaginable violence and scale, in an enterprise that had no intention of producing you and yet produced you anyway. The supernova that scattered the iron now in your blood did not explode in order to make life possible. It exploded because gravity won a battle it had been fighting for millions of years against a core of iron that had reached a critical mass. The fact that the scattered iron eventually found its way into a living being was not a purpose, it was a consequence. And yet here you are, aware of the process, capable of reconstructing it step by step, from the physics of nuclear binding energy to the chemistry of hemoglobin, to the biology of oxygen transport, to the neuroscience of the awareness that is, at this moment, reading these words and understanding them. This is what makes the story of Stevenson 2 to 18 something more than a record in a catalogue of extreme objects. It is a story about the cycle that produced you. The star is not a curiosity sitting 19,000 light-years away, unrelated to your existence. It is a future participant in the same process that has been running since long before the Earth formed the process of stellar birth, nuclear burning, violent death, and elemental dispersal that continuously enriches the interstellar medium and provides the raw materials for new generations of stars, planets, and whatever arises on those planets. When Stevenson 2 to 18 finally explodes, whether the light arrives in 9,000 years or 19,000 years or 30,000 years, the elements it scatters into the Scutum Centaurus arm will begin a journey. Some fraction of them will drift through the interstellar medium for millions of years. Some fraction of those will be swept up in the collapse of a molecular cloud and incorporated into a new star system. Some fraction of those star systems will have rocky planets in habitable zones. Some fraction of those planets will develop chemistry. Some fraction of that chemistry will become complex enough to cross the threshold that separates the non-living from the living. And some fraction of what lives, if the universe continues to operate the way it has operated for the past 13 billion years, will eventually look up. We do not know what they will look like. We do not know what instruments they will use or what questions they will ask or what framework they will use to organize their understanding of the cosmos. But if they look at the sky above their world and trace the origins of the atoms in their own bodies, they will find, at the end of that chain, a violent death, a core collapse, a shockwave racing through an envelope larger than a planetary orbit, a dispersal of elements into the dark. They will find Stevenson 2 to 18, or something very much like it, at the beginning of their story. Just as you find it, looking backward, somewhere in the middle of yours, the light from the death of this star is either already traveling or has not yet begun. The iron core is either accumulating toward its limit or has already crossed it. The shock wave is either still racing through the stellar envelope or has long since deposited its energy into the surrounding interstellar medium and faded into the background radiation of the galaxy. We do not know which. We will not know in our lifetimes. We will not know in the lifetime of our civilization as it currently exists. The answer is sealed inside a sphere of light that is either somewhere between here and Scutum or has not yet been emitted, and there is nothing we can do to retrieve it sooner than the speed of light permits. But we know what is coming. We know the physics. We know the sequence: iron, collapse, bounce, shock, explosion, dispersal, with enough precision to trace the consequences forward and backward through time. We know that the elements now locked inside that dying star will, in some form, outlast the star by billions of years. We know that some fraction of those elements will find their way into structures of extraordinary complexity. We know this because we are the proof that it has happened before. You are not waiting for Stevenson 2 to 18 to die. You are the evidence that something like it already did, billions of years ago, in deaths we will never observe, in explosions whose light has long since faded past detectability, in dispersals that seeded the region of the galaxy that eventually became our solar system. The same process that awaits the largest star we have ever found already ran to its conclusion many times in the stars whose deaths made your existence possible. Every breath you take is a receipt for a supernova. Every heartbeat is powered by iron that was forged in a dying core. Every thought you form, every synapse that fires, every neuron that carries a signal from one part of your brain to another, every moment of awareness you have ever experienced runs on chemistry, assembled from the ash of stars that never knew they were building anything. Out there, 19,000 light-years away, buried behind dust that makes it invisible to the naked eye, pulsing slowly in the infrared darkness of the Scutum Centaurus arm, the largest star we have ever found is dying. Its iron core is accumulating, its silicon is burning, its outer envelope, vast beyond any analogy drawn from the scale of the solar system, drifts and sheds and glows in ignorance of the countdown occurring at its center. It does not know what it is building. It does not know that the elements it will scatter into the dark will travel for millions of years through the cold between the stars. It does not know that some of those elements will find their way into something that wonders. But we know, and the knowing the capacity to trace this chain from a dying iron core to the blood moving through your body at this moment is perhaps the most extraordinary thing in the observable universe. Not because it answers every question, not because it resolves the uncertainty about the star's true size, or tells us exactly when the explosion will come, or tells us what lies at the center of the neutron star or black hole it will leave behind, but because it means that the universe, through the long and violent process of its own evolution, has produced something that looks back at it, something that measures it, something that understands, at least in part, what it is doing. The light is coming. It does not know we are waiting, but we are here, and we are made of everything that came before it.